All right, so we're going to start looking at energy now, chapter 5 here. So, chapter 5 just looks at an overview of energy. So, within this, within living things, we see two major processes that occur: photosynthesis and cellular respiration, uh, as our mechanisms and how we use energy as living things. So, we see the ultimate source of all energy on Earth is the sun. Now, there are a few exceptions when we look at like hydrothermal vents, but for the most part, we're looking at the sun. We have things like plants and phytoplankton that do photosynthesis, taking that energy from the sun and turning it into chemical energy. And then within consumers, things that eat plants or other organisms, they're going to do this process of cellular respiration, where they break down those chemicals, those typically glucose molecules, to get energy out of that. So, what is energy? When we look at energy, this is the capacity to do work. We've got potential energy, which is just stored energy. This could be gravitational potential energy, something sitting on a cliff that has the potential to gain energy as it moves. Or it could be chemical potential energy, which we kind of focus on here when we talk about living things, and that's the energy stored in bonds of molecules. Then we also have kinetic energy. This is the energy actually being used to do that work that needs to be done, whether it be movement, breaking down other molecules, and so on. Okay, so we see this apple here. Within this apple, we've got all these molecules, and in each of those bonds, we've got chemical energy that is stored there. So when we eat things, we break those bonds of these molecules to get the energy that we need, and then we convert it into another form, which we'll talk about in a little bit. Here's an example of potential and kinetic energy. As the girl's at the top of the slide, she has that gravitational potential energy. Then as she goes down, that potential energy is turning into kinetic energy. She's moving. So energy flow is governed by thermodynamics. So we've got our two main laws. There are more than this, but we're only going to look at these two. So the first law of thermodynamics, the law of conservation of energy. Basically what we see here is that there's a limited amount of energy. Okay, you can't create or destroy matter or energy. It's got to come from somewhere. Okay, so what we see is this flow of energy is just the changing of form through these processes of photosynthesis and cellular respiration. The second law of thermodynamics, we're looking that all things in the universe are moving toward entropy, this measure of disorder. So basically, we see that without any energy input, things like molecules will start to break down. They'll separate from one another. Okay. And so we see heat from an engine. And basically what we notice is that, say you put 100 units of potential energy in your car, you burn that fuel for that energy. 25 units get turned into energy to actually move the car. 75 units are turned into heat. That heat does you no good. It's energy that's essentially lost due to this entropy, this movement toward disorder. So we see that no reaction is 100% efficient. In fact, most are actually very inefficient, as this example shows. And so here is kind of the go-to illustration of entropy, right? This disorder happens spontaneously. Just in your everyday life, your room becomes a mess. But in order to get it back to that normal, that organized state, you have to use energy to get it there. And this is what we see in living things, is that energy has to be used in order to maintain living things, because they'll break down without it. So we ask ourselves, if everything is moving toward this entropy, everything is going toward this state of disorder, how do things continue? How does life go on? It's the sun, right? We have that constant flow of energy coming to Earth from the sun. and then it just goes down those trophic levels, right? We're starting at our producers, these things that do photosynthesis, then that energy is transferred to these other levels by these organisms consuming one another. Okay. So we see here in a chemical reaction, we've got a standard reaction here, A plus B yields AB, right? We've got our reactants on the left here, products on the right. So here we see this process of dehydration synthesis, which we talked about when we talked about molecules, right? You take out the water to build a bigger molecule. Okay. And so here we see in cells, we've got a lot of methods in how we do these reactions. So we've got two types of reactions, exergonic and endergonic. Exergonic reactions will release energy, endergonic absorb energy. So sometimes our cells will use an exergonic reaction, which releases energy, and then use that energy for an endergonic reaction, and this is coupled. So we pair these reactions together to utilize that energy as best as possible. There is a major molecule within all living things that is used as the currency of energy. So when we eat and we break down the molecules of food, typically we don't use that energy immediately. What we do is we store it in the form of ATP, this adenosine triphosphate molecule. So here we see our ATP. We've got our adenine, our nitrogenous base here, a ribose sugar, and then 3 phosphate groups. Within each of these bonds between the phosphates, there's a lot of energy stored there. So if our cell needs energy to move a molecule across the membrane or cause some reaction to happen, it will break one of these bonds, create this ADP, a diphosphate, because we took away one of the phosphates, and use that energy from breaking that bond for whatever it's necessary for. And we see that this ATP is used more than any other molecule for the sake of energy in our bodies. Okay. So essentially what happens is we have this exergonic reaction. Let's say we're breaking down food in our body. We take a phosphate, put it on an ADP, it becomes phosphorylated, and we've got our ATP. Then we need some other reaction happen that's endergonic. And so we'll break that phosphate off that ATP, use that energy for whatever we need it for. Okay. We have some other energy carriers. These specifically will carry protons and electrons, and we'll see these quite a bit in photosynthesis and cellular respiration. We have NADP, which becomes NADPH when it has that proton, that hydrogen. And this we just see in photosynthesis. So when you see this P, photosynthesis, NAD and FAD, we will see some in both processes, sometimes in just one of those processes. But we use these a lot to help produce those ATP molecules, and we'll talk about those in chapter 6 and 7. And then the vitamins that you need to make sure you can produce this NAD and FAD. You need your niacin and your riboflavin, so on. Okay. You cannot fry your cells by getting bond energy out of sugar bonds. Okay. There's a limit to how much energy is being created or released, at least. However, it takes a lot of energy to break these bonds. So we use a special class of proteins known as enzymes that are biological catalysts. Lowers that activation energy, so we don't have to utilize quite as much energy to make the reaction happen. So things that we know about enzymes, they're catalysts. They're going to speed up reactions. They're reusable, so they can cause the same reaction to happen 100, 200 times. They lower the activation energy, so our cells don't have to use as much energy to make a reaction happen. These are typically proteins, and they're very specific. Only one type of reaction is going to occur per enzyme. Okay? So this just shows we've got our enzyme, we've got our active site here, and that substrate fits perfectly in there. And it will be the only type of substrate that should be able to fit within that enzyme. Okay? And that's chapter 5. The next video, we will be looking at photosynthesis.